Alrighty, let's try another streak. So I did end up thinking a lot about the hard one from yesterday, and I just couldn't come up with anything that worked. Thought a lot about it though. Anyways, destroying asteroids solved previously, I guess. Medium. You're given an integer mass, which represents the original mass of a planet. You are further given an integer array of asteroids, where asteroids at I is the mass of the ith asteroid. You can arrange for the planet to collide with the asteroids in any arbitrary order if the mass of the planet is greater than or equal to the mass of the asteroid. If the mass of the planet is greater than the mass of the asteroid, greater than or equal to the mass of the asteroid is destroyed and the planet gains the mass of the asteroid. Otherwise, the planet is destroyed. Return true if all asteroids can be destroyed. Return false otherwise. Okay, so it's kind of like eating asteroids. So 10, you eat the 3, become 13, eat the 5, become 18, eat the 9, become 27, eat the 19, become something. Okay, yeah. 5 eats the 4, becomes 9, eats the 4, becomes 13, eats the 9, becomes 22, does not eat the 23. Okay, this is pretty simple. 10 to the 5th is the length of the array. Seems like you just sort and try to eat in order. I'm not sure why you wouldn't eat in from smallest to largest. What the heck? This is medium? Why is this a medium? Unless you can't sort, or unless sorting is too slow. I don't think sorting is slow. Well, can you do it in linear? Can you do it in linear? You can also do a heap, I guess. I mean, I'm gonna try sorting it. Sorting might be slower than a heap, but let's try. Asteroids.sort. Let's say for n is equal to length of the asteroids array, for k in range n, if mass, so it's going from smallest to largest, and if at any point the mass is bigger or is smaller than the kth smallest, then it's going to not work because it's not going to be able to eat it. So if mass is less than asteroids at k, return false. Otherwise, the default is just me adding in the asteroid's mass. And then returning true once it's completed with the array. Okay, I mean, this might be slower than a heap, but it should work. Okay, sure. I mean, I don't think you can do it in linear time, right? I don't think this can be done in linear time. Can it? Let's try doing heap. Basic method using sorting. Eat smallest to largest. And that guarantees that you should always be able to grow bigger if possible. Alright, so let's go heap. Heap is going to be, heap is generally sorted by smallest, so it's generally a min heap. So for, let's say n is the length of the array, for k in range n, this going to be any better? Probably, right? Probably. For k in range n, I think I add it to the heap. Add whatever the element is here. Heap dot or let's see, heap push the current size of the asteroids, and then while the smallest is edible, while mass is greater than or equal to asteroids. Is it greater than or equal to? Yeah, greater than or equal to. Greater than or equal to the top of the heap, which is the smallest element. Heap at 0. I guess I don't want to eat the biggest one. Maybe I need to have infinity on the heap, because I don't want to check for the fact that this is going to be an empty heap. So maybe I'll have infinity on the heap. Then mass plus equals heap pop, the top of the heap, the smallest element. And then this iterates until the very end. And I think at the very end, if there's more than just infinity on the heap, then that's the no-go. So return, it finishes eating everything if the size of the heap is just infinity. So if the length of the heap is equal to 1. All right. How fast are you, buddy? So, boy. Okay. Slapped down, slap down. Huh. How to speed this up? You're given mass, which represents the original mass. You're given further an integer array. I mean, interesting. 3, 9, 19, 5, 21. 3, then 5, then 9, then 19, then 21. Yes, maybe skip adding it to the heap if it's already smaller. Right, skip. The heap is only there for something that's bigger. So don't push onto the heap automatically. Okay, so something like this. If so, assume that you want to eat it first. So if the mass of the object is greater than or equal to the current asteroid, mass increases, and at that point see if you can eat more of the heap. Otherwise, if it can't eat it, then that's when you push. Maybe this is how I should be doing it, because otherwise this can be always pushing onto the heap when you could just be eating it. I think this might work. Or I think this is faster at least. Okay, I'm getting back to the original speed of the basic method. Heap is infinity. Every element, I guess I guess it is faster rather than use an index loop. I can use a for each loop, right? Because I don't really need to know the index. So for every m a mass, asteroid mass in asteroids, if the mass of the planet is bigger than or equal to the mass of the asteroid, increase the planet mass, and then if it's bigger than the smallest element, add it, else push the asteroid mass onto the heap. Okay, I mean, I'm fairly sure that the for each loop is faster. Not sure how much faster. 5 milliseconds faster. So it's like 5%. Okay, I'm going to try also changing this one. And let's go ahead and quickly test the speed. Whoops, this is the asteroids array. I'm guessing it's not going to be that much better. Although it is better, just using that for each loop. I mean, if I gotten this as my original speed, would I care to try to improve it? Is it improvable? I don't know that you can really improve it that much. I mean, I thought the heap would in theory improve it, because rather than sorting it, which is n log n, you're using like n log k, where k is the size of the heap at any given point. Maybe it's just optimization wise better to sort rather than have to deal with a bunch of heap operations. Because a heap does have like a binary tree behind it, even though in theory it's faster. In practice it's slower. I mean, you really do want to eat from the smallest to largest. Really do want to eat from smallest to largest. And the earliest you can stop is when you can detect that you can't eat. Or mass use. Yeah, I mean, this is in theory the fastest I can think of. While mass greater than or equal to heap is 0. We push I mean, I guess this is kind of slow. It's as slow as any other heap operation, to be honest. It's O log k, right? It's like log of the size of the heap. Or, yeah, log the size of the heap. Alright, anyways. Yeah, I'm done. So, not really sure how to get faster. To get faster than using sorting / heap in the most simplest answer kind of method, use sorting, since if the planet is eating the smallest to largest asteroid, that is the easiest way to accomplish eating all the asteroids. If at any point it fails to eat the kth asteroid, then there is no other way for it to accomplish the goal of eating all the asteroids. So, kind of short circuit, return false in that case. Otherwise, return true after finishing all the asteroids in the sorted array. In theory, I believe the heap method is faster, but implementation-wise / in practice, heaps, a single heap doing this is not faster versus a single kind of array sorting. If it was maybe really large, like the list was really large, instead of asteroids being 10 to the 5th, maybe like 10 to the 6th or 7th, maybe that's when heaps might overcome. Time complexity can be O of n log n for sorting method, because obviously you need one pass to do the mass accumulation after sorting it, and O of n log k for the heap method, because at any point you should only have log k to insert into the heap or to pop out of the heap. Yeah. Sorry. To pop out of the heap, it should be O of 1. To push into the heap is going to be O of log k. Space complexity is going to be, actually, is that right? I'm pretty sure that's right. Maybe it's O of 1 for heap to see what the smallest is, and O of log k to remove the smallest, actually. I have to double check that if I really cared. Space complexity is going to be O of 1 for sorting method, and O in theory it's going to be O of n for heap method, since in the worst case you need to store the whole heap. Store a heap of size n. Yeah, okay.